I just, a few moments ago, posted our first homework assignment. It's going to be due on Wednesday, so you'll have some time for that. But the homework assignment has been posted at the class website, which you can see. You can get there through Blackboard, or you can also follow the QR code that's on the syllabus. So check them out. Feel free to work on it with your friends if you like, although everybody's got to, you have to hand in your own paper, but if you want to work together on it, that's totally fine with me. Any vague question about the homework? I mean, I think it's pretty straightforward. Answer the questions. All right, great. And I hope that everybody has figured out how to get into Gradescope by now. I'm pretty sure that everybody submitted their interesting facts, so thank you for those. They were very interesting. Some were more interesting than others, if I'm being honest. But thank you for all those. All right, great. Let's get on with it then. We are gonna start the first of our non-review topics, although, there was one other thing I wanted to mention, and that is, I said this on the first day of class. I'm just going to say it again. I teach 2 sections of this class. The other one meets right after this one, and the other one only has 20 students in it. This one has 28, so there's not a lot of extra seats in here. So if you ever feel like it's too crowded or something, feel free to come to the other one. It's also too hot in here, but I don't know what to do about that. Sorry about that. All right, let's talk about the area between curves. This is the first of the main things that's on the big list. What we've done so far, I consider to be all review topics, and I kind of assume that everybody has seen those before. From now on, I assume that you haven't seen this, although realistically speaking, I know that probably many of you have seen this, but I'm going to go through it as if nobody knows what I'm talking about yet. The area between curves. What I'm referring to is if you have 2 functions, something like this and this. Let's say this is f of x and g of x. The area between curves, like from A to B, means this. Just what you think it means. It's this area in between the curves, right? And a typical question from this section is just like, I give you specific functions, and your job is to find the area between the curves. These are weird shaped areas, all right? We're going to do this similarly to how you find the area under a curve. The area under one curve is just the integral of that function from A to B. This is kind of, almost the same. Really, the way we think about it is we think like so. You take this area, I'm going to try and redraw just the shaded part, right, on my picture. Doesn't really matter what it looks like. It looks something like that, right? It has a weird curve at the top and also a weird curve at the bottom. But the standard way that we always think about the integral for measuring weird shapes or whatever is you imagine that you chop this original weird shape into a whole bunch of little rectangles, and then you add up those rectangular areas. So we add the rectangle areas. I hope everybody remembers the basic idea. This is like the basic idea behind all of integral calculus. You add up the rectangular areas where the base of each one is like very small. We usually call it delta x down there. That's like this itty bitty little width of each of those rectangles. And then what are their heights? Their heights in this case are given by the 2 functions. Like the top is, I called it before f of x, and the bottom is g of x, right? So the base of each one is delta x. The height of each one. How would I get the height if I know what f and g are? Yeah?
F of x minus g of x.
Yeah, you would just subtract them. You do the top function minus the bottom function. Because these are y coordinates, the y coordinate of the top minus the y coordinate of the bottom tells you how tall it is. So the height of each one is f of x minus g of x, right? And what do you get when you sort of add all these rectangles up? You add them up like, if you really had to do this, it would look something like I would do something like x sub I minus g of x sub I, and then that's the height, and then the width is like that. This is the, I'm sure you've seen formulas like this. This is what we call a Riemann sum, and then you would do something like limit as delta x goes to 0. Something like that. This, though, the whole point of talking about Riemann sums, and this is something that I assume you went over in your old class, and we're not going to actually, in this class, we're not going to calculate Riemann sums directly. This adds up in the limit, I'll say in the limit, it adds up to integral from a to b f of x minus g of x dx. This is kind of how Riemann sums work. Whatever the function that you have inside, here ends up just being the function inside the integral sign. And then when you do this limit, it's kind of like the delta x turns into dx, and the summation sign turns into the integral sign. That's at least the sort of surface level description of how a Riemann sum turns into an integral. Like I said, I don't really want to get into the details of that, but that's why this is just the integral of f of x minus g of x. You think of this difference of the two functions representing the heights of those little rectangles as you move across the shape. All right, anyway, this is, I suppose you need to memorize this formula. Not much of a formula, but this is the area between curves. And f of x, you have, as part of this, you have to remember f of x is the bigger of the two functions. That is to say, when I say bigger, I mean higher y value, and g of x is the smaller. All right? This, if you like, is big E minus smalls, as I say. My kid is taking calculus in high school, and I said this. He said, yeah, we're doing the area between curves. I said, oh yeah, big E minus smalls? And he said, yeah. And then like 10 minutes later, he said, you don't actually say that to your students, do you? I said, yeah, I do. I know, it's stupid. I'm not afraid of saying stupid things if it helps you remember. I don't know if this helps anybody remember. It's big E minus smalls, the larger function minus the smaller function. All right, that's the area between curves. Not a hard formula to use when it comes to, doing homework problems or whatever about area between curves. Usually the hard part is kind of figuring out how to set the whole thing up. But doing the integral is not so bad. So let's try, I got a bunch of examples. Let's try one which doesn't really require much setup at all. How about, here's one example, the area between the functions x and x squared, where they cross each other. All right, I suppose this one does require a little bit of setup. You have to kind of know what these things look like. Now, when I'm giving these problems, like on a quiz or on a test or something, if it's a really weird function, I'm just going to show you the picture because you're not going to be using calculators, remember? So ordinarily, if it's on the homework or something, you might want to graph the functions just so that you can see what they look like. I am not going to assume that you know how to graph super weird functions. But anyway, everybody should know how to draw these, right? This, I think, would be totally reasonable to ask you to do without a calculator. X is just this, right? This is y equals x. And then x squared is a parabola, and it does like that. All right? So the area between them is that little sort of slivery thing. This is what I'm talking about here. All right? That's the area I want. So we are going to do the integral of the larger minus the smaller, right? It'll be integral of the bigger, big E minus smalls, as I say. Which one is big E in this case? X, yeah. Usually x squared is bigger than x, but when I'm talking about this region right here, the larger function, that is the one higher up in the y-axis, is x, and then the smaller function is x squared. So it's going to be the integral of x minus x squared dx. This is a fairly simple integral to do, although we do have to figure out what are the little numbers here. So what are a and b in this case? Like the numbers that go here and here on the integral, all right? And in this case, this example is not so hard to do that, but remember the a and the b, they represent sort of the leftmost end of the area that I'm talking about and the rightmost end. So here, I can tell right on just by looking on the picture, that's 0, right? The leftmost side of this area, if the picture ain't lying, is 0. So a is 0. What about the b? That would be this value right here. So this one is the a. What about this one? I want the x coordinate of this value. That's the b. Anyone happen to know? This would be some number where x and x squared give you the same number, but not 0, because I already put 0 on the other one. What do you say? 1, yeah. 1 is also the other time when these two curves intersect. So that is b equals 1. Now this one is fairly easy to just kind of like common sense your way through it and figure out what those 2 points are. You can just tell by looking, the left one is 0, and then the one on the right you can easily figure out. Although, if it were more complicated and you weren't able to do this kind of common sense, can anybody say how would you actually work this out if you had to work it out without sort of knowing the points? Yeah.
You'd set x squared and x equal to each other.
Yeah, so you would set those equal to each other. Now in this case, like I said, it's not really necessary, but just for the sake of knowing how to do it, to find the intersection points, which are important, as usual, we set the equations equal to each other. So I would say x squared equals x, and then solve that for x. You're going to get 2 answers because this is a quadratic. So this would, if I had to solve it like a quadratic, I would put all these guys on the same side and then factor. And now this says x equals 0 or x equal 1, right? So, and those are my, the 2 ones that we found just by common sense before. All right. Anyway, let's do the whole thing then. All this was basically just a setup. It's this integral from 0 to 1. So the area is the integral 0 to 1 x minus x squared dx. And this is an easy integral to do. It'll be 1/2 x squared minus 1/3 x cubed. Plugging in 0 and 1. So I get 1/2 times 1 squared minus 1/3 times 1 cubed. Subtract, and actually everything's going to be 0 when I do this part. 1/2 times 0 squared minus 1/3 0 cubed. All right, that's the answer. It's basically 1/2 minus 1/3, if you like. I don't care if you simplify it. 1/6. All right. Any thoughts about that? Okay, this is, I don't know, this is kind of slightly interesting, at least to me, that actually equals 1/6. The area of this weird sort of curvy thing is 1/6. That means if you put 6 of those together, it adds up to like a unit square, which is a little strange, just because, like in real life, this is a curved edge. If you put 6 of them together, it's actually not going to make a square, but whatever it is, it adds up to area 1. It's a little, I don't know. That seems a little strange to me. Those are the things that I think about sometimes. Any thoughts about that? All right. I feel like if that area really is 1/6, it means I should be able to take 6 of them and somehow put them together into a square. It's not really possible, like physically speaking, to do that, but because they're curvy. All right. If I see curvy things, just like in normal life, I assume their area has something to do with pi times something or other, because that's like usually curvy things are like that. But no, actually, not all curvy things are like that. All right, let's try another one. Like I said, I hope you agree. Like the integral in these problems, the integral is usually not very difficult to do. It's a matter of setting it up properly. That's usually where you're going to expend most of your effort. Let's try this one. Find the shaded area. Oftentimes you'll just like be given a picture and your job is to find the appropriate shaded area. So this one is somewhat strange. I have this here. This is y equals minus x, and then I also have this here. Y equals 2x plus 1, and I want you to find the shaded area, like so. This and this. All right? That shaded area. This is your job. This bow tie type shape. All right? So there are a few things to consider. The most obvious thing is what I see here in terms of the shaded area really sort of consists of two different regions of the bow tie. There's kind of like the triangle on the right and the triangle on the left. And we must consider them separately. You actually can't do this one using just one integral. And the main reason is because sort of the biggie and the smalls shifts in the middle. Like on the right-hand side, this one is on top and this one is on the bottom. But over here, this one is on top and this one is on the bottom. And so you have to break this into two separate parts. So we're going to do the two triangles separately. And the reason we have to do that in this case is because, I'll just say, since the lines cross, which means there isn't one that's always the bigger and one that's always the smaller, right? Because it changes in the middle there. So we're going to do the two triangles separately because the lines cross, and we better actually figure out where actually do the lines cross, like that point right there. It's actually not at the origin. It's kind of close to the origin on my picture, but I didn't mean for it to look like it is at the origin. So let's find the crossing point. And we do this as usual by setting the two equations equal to one another. So it's going to say 2x plus 1 equal negative x. And then solve for x. It's look like I'm going to get one answer, which is good because there's 1 point I'm looking for here. So add this over. I get 3x equals minus 1. Just moving the business around. X equals negative 1/3, which actually looks reasonable on this picture, right? So that's where this point is right there, minus 1/3. All right? And so now we're going to do the two triangles separately. We just have to do one integral for the right side and one integral for the left side. So let's do it. So how about this one first? This one is, can we give me the integral here? Integral from something to something of something, something, something? What do you think? Yeah?
The integral from -3 to negative 1/3.
All right. I think I'm trying to do the one on the right.
Oh, okay.
Sounds like you're.
Negative 1/3. The integral from negative 1/3 to 2.
Yeah.
Over parentheses 2x plus 1 close parentheses minus negative x.
Yeah. Excellent. Great.
Yeah.
Yeah. Great. Yeah. This is the bigger one, which is on this side. The bigger one is the 2x plus 1, and then minus the negative x on the bottom. Excellent. And let's work that out. So actually, these first parentheses around 2x plus 1 don't matter because everything in there is being added. The other parentheses kind of matter because of the minus minus, but this just ends up being minus 1/3 to 2, 2x plus 1 plus x, which is 3x plus 1. Might as well simplify as much as you can inside the integral sign. So 3x plus 1 dx. And then we're going to do the integral. It becomes 3/2 x squared minus, no, plus x, right? Minus 1/3 and 2 up there. How am I doing? And then we plug the numbers in, you get whatever you get. 3/2 times 2 squared plus 2 minus 3/2 times negative 1/3 squared plus negative 1/3. All right, that's my answer for the first half. Well, the half on the right. Any thoughts about that one so far? All right, and what about the other side? The other side is similar. The endpoints, this time for the left side, the endpoints are going to go -3 up to -1/3. And then the biggie and the smalls are the other way around. So for the other one, it shall be, that's this one now. This one is -3 to -1/3. And I write the functions the other way around. It's -x on top minus 2x plus 1, which is the smaller function. And here actually those parentheses do matter. You should distribute the minus sign when you combine that stuff together. I think it's going to be -3x minus 1, right? And then we do the integral as before. It's similar to what we did for the first half there. So it's going to be -3/2 x squared minus x. Plug in -1/3 and -3. -3/2 -1/3 squared minus -3. Negative. Plug in a third first to both of them, -3, and then subtract. And then go through again, plug in -3. -3/2 minus 3 squared minus -3. There you go. All right, this is the other half of the bow tie shape. And what's our final answer? Yeah?
The top one plus the bottom one.
Right, the final answer is the sum of all of that plus all of that. Whatever those are. So I would just say the total area is, this is annoying to write. Would you mind if I just sort of do this plus this, right? It's totally fine with me. If you're doing the homework or something, you want to write that, you don't have to rewrite the whole thing. If you're using a calculator all the way throughout, you could just calculate this and also calculate this and then add them together. No big deal. But if you're not using a calculator, it's a pain to write. All right. Excellent. So this one you had to work a little bit to set it up and split it apart into 2 pieces. I have some for you to try, but I got one more first. There's one other way in which you might have to do some slightly weird business in order to set it up. Let's try just one more, and then I'll have some for you all. How about, this is y equals 1/2 x. And what's weird about this one is the other is a parabola that way. And this parabola, its equation is x equals y squared minus 3. And I want the shaded area there. I'm gonna draw this parabola again just because. So if you actually graph this, say on a calculator or something, you'll see the vertex of that parabola is sort of fairly far to the left, which kind of does make a difference, all right? But anyway, this is the area that I want. All right. Now this time, the traditional like biggie minus smalls thing doesn't actually work very nicely because, for example, like right over here, that would be the height. Actually, there's no problem there. The bigger is the parabola part, and then I subtract the smaller, right? But actually, if you look further to the left, things are going fine around here, but when you're over here, we got problems. Say these 2 points. What's wrong with that in terms of the big and the small?
You're calculating the height based on its own curve.
Yeah, it's the same curve both times, the bigger and the smaller. And so what are you going to do when you subtract the bigger minus smaller? You get 0, I guess. But that distance I drew is not 0. So this is not going to work. Anyone know the appropriate thing to do in this case? Yeah.
Do left minus right.
Yeah, you do it kind of sideways. Instead of the bigger minus the smaller in terms of the y values, you do the bigger minus the smaller in terms of the x values, which ends up being the value on the right side minus the value on the left side, right? So this, it's still kind of the bigger minus the smaller. So I'm gonna erase. Ooh, I went too far. Don't do like this. I'm gonna say. Usually the tip off here is when your curves are functions of x in terms of y, right? You probably knew something weird was going to happen as soon as you saw this, x equals y squared minus 3. That's a little strange. When your curves are functions of x in terms of y, we do everything kind of sideways. That is, I'm going to think of this as, instead of little heights going vertically, I'm going to think of it as little, I suppose, heights, but they're going horizontally this time, all right? And so the bigger minus the smaller becomes the further to the right minus the further to the left, which does, that still is bigger x value minus smaller x value. So this time we do everything sideways. What I mean by that is, like practically speaking, this means write all functions in terms of y. Now in my case, the second function is already written in terms of y, this one, x equals y squared minus 3. The other one isn't, but you could rearrange it and make it so that it is, so that'll be fine. Write all the functions in terms of y, and then do the integral as a dy. When you do the integral, the variable inside the integral is going to be y, not x, all right? And the bigger and the smaller, the bigger in this case means bigger x value, i.e. further to the right, and the smaller means further to the left, all right? So it's still the bigger minus the smaller, but it's in terms of x values now. And the little a and the b, the boundaries on the integral, they should be y values, not x values. It's just everything you do in terms of y values instead of x values. All right, so let's see if we can make this happen. I have my two functions. They are y squared minus 3. This other one, maybe I have a lot of words here. Would you mind if I'm just going to copy this down so I can scroll away from the words. So here, first of all, I'm going to write both functions as y in terms of x. X in terms of y. So this one, I'm going to solve for x. It says x equals 2y. That's by multiplying the 1/2 over to the other side. And the other one is already the way I want it to look. X equals y squared minus 3. Can anybody say which one is the bigger and which is the smaller? Yeah, the straight line is the bigger, all right? I'm thinking of bigger meaning further to the right. So this is the biggie, and this is the smalls, RIP. So we're going to subtract them inside of the integral. It'll say the bigger minus the smaller. And then we also need the integral endpoints. That would be the y value of those two numbers. So it's like this is the a. Sorry, that's the b, because they're y values. The a is the smaller and the b is the bigger, right? From a up to b. And what do you say? How do we find the a and the b here?
Subtract the 2.
That's not what I was going to say.
You set them equal to each other.
Yeah, you set equal the two functions, just like we always do.
Yeah.
So I have x equal 2y, and I also have x equal y squared minus 3. So I set those equal to each other. So these are for the endpoints. Hopefully I'll get two solutions. 2y equals y squared minus 3. Right? I'm setting them equal to each other. This is a quadratic, so I'm going to factor, and I should get two solutions. That's what we want. So maybe I'll put them all on the right-hand side. I hope everybody remembers how to factor this kind of business, like so. And then this is y minus 3, and y plus 1. And so my solutions are 3 and negative 1, which looks reasonable on my picture, right? The A is minus 1, the B is 3. All right. So I think we have all of the correct ingredients to set it up. And as usual, the integral itself is not really going to be very hard to do. So it's going to be integral minus 1 to 3, because those are my two endpoint values. And then I go bigger minus the smaller. The bigger is 2y, minus the smaller is y squared minus 3. Make sure you put those parentheses there matter, because you're going to have to distribute the minus sign. Let's do that, distribute the minus sign, and then do the integral. And that should do it for us. 2y minus y squared plus 3 dy. Sorry, I wrote dx there. I should have wrote dy. It doesn't really make sense to put dx in there. I'm talking about functions of y. All right, do the antiderivatives. We got, this is just going to be y squared minus 1/3 y cubed plus 3y. And plugging in minus 1 up to 3. Right? I'm feeling good so far. And so we just plug in the 3 and then subtract and plug in the negative 1. So this, I guess this will be my answer. 3 squared minus 1/3 3 cubed plus 3 times 3 minus, and now plug in negative 1. Negative 1 squared minus 1/3 negative 1 cubed plus 3 negative 1. There you go. This is our answer. Any thoughts about that one? I hope that it worked out for you. In my opinion, the integral is the easy part. The hard part is the rest of it. It's not that hard, but if part of it is going to be hard, that's the part. All right, I got some for you to try. So another thing that can make this, I guess, slightly tricky is just like you're going to have to decide for yourself what you have to do. Like, you know, here you have to split into two parts. Here you have to do it sideways. It's up to you to decide which method is appropriate. Anyway, I got 2. Find the shaded area each time. Try to draw these nicely. The shaded area is here and here. All right, so we have a parabola and a straight line, and I want those areas there. Okay, that was one, and another. All right, these are 2 separate problems. See what you think. I'm going to come around and see how you do.
How are you able to just draw that line across?
Here?
Yeah.
You mean like where is it?
Yeah.
It's at the y-intercept of this one,
Okay.
which you should be able to find.
Okay.
Yes, sir. Good. You're not wrong. I mean, this is just great. Because remember, this is how you find the intersections of two lines. Say one intersection, which is like. Good. Yeah, you just have to find the white out here and the white out here. Still good here? Calculate here. It's a flex. Still good on there? Still good here? Yes. Still here? Calculating.
It's around the factor.
I think.
I did this one. Minus the
No, no, it's one good. This actually doesn't factor.
Yeah, I was really
confused. Remember, the reason you do this, you set the two things
Yeah.
next to each other. The reason you do
So you
that
make it
is
X
find the
equals Y
intersections
one.
of two curves.
Oh, they don't understand.
Yeah, these ones don't intersect, so you should be.
Okay, yeah, I was really confused. I was like,
You still have to find the, like, the bottom point and the top point, but
Okay.
it's easier. This way.
Once we set up both of them,
Yeah.
then we subtract.
You would add the two answers, like this represents the area of one of them, this represents the area of the other. Yes.
Oh, they it's 0, 1,
It's easier.
It is.
Can I just say something about this? Because,
Oh, I already did it.
when you do the integration, this should be like.
Yeah.
Yeah.
Doing good here?
So, use that negative one or just like 0 and 1?
They should be values of y on the bottom.
Okay.
So yeah, the x value goes back to -1, but
Oh, yeah.
Still good here?
It's like bigger and smaller. Oh, like there's like a red. So like the first part, like this axis.
Did we just add
Oh, okay. Like this triangle here, you pick like a random x value, and like on here, which curve is going to end up having a higher x, y value at that point? Like which one's
Yeah.
over here, switch.
1/3 minus 1 times 1.
Yeah, I never actually. I would just leave it at that. I don't really care. Yeah, I mean, I assume that, no, because they don't intersect. That's just like, I feel like this class is not about it, but, you know,
It starts because you're going top and bottom, it starts at 0. Yeah. And then you see the line at x plus 1. Well, you said it, you have minus 1.
How's it going?
Oh my God.
Can I give you some advice? You should start finding these two things. But so you do this, like this, and you gotta solve for
Percent equal, but also like you don't really need to if they're not exercising. I don't think you can. So what you're gonna do is this is the intersection point of it being and it's a y line. So that happens at x equals 1. So this is hard to zero.
Actually, this
So
was
both of those here.
remember the
I'll say it's the same.
is to find the intersections of the two rows.
That's what I was thinking. If you remember, like, the formulas like pi cubed over 3.
Right, that's the. So that's why the factoring is.
That's a given.
So it's not.
Yeah, I didn't know that.
You just have to find, what you wanna find is the y value.
Yeah.
All right, can we talk about these? As I was going around, people did pretty well with the first one. I know some people haven't quite finished the second one. That's all right. The first one, we must find, first of all, these points. Now, I wrote 1 and 3 here, although I hadn't written those at the beginning. You have to figure that out. The way to figure that out is these 2 points are the intersections of this curve and that straight line. And so you set the 2 things equal to one another, which I did right here. The line equals the curve, and then I have to solve this for x. That's a quadratic, so you should like put everything on one side and then factor. So that I do like so. I factor like x minus 3 and x minus 1 equals 0, which means x equals 3 and x equal 1 are my 2 solutions. So that's how you know what those 2 x values of 1 and 3 are. And then you set up your integrals. The first, so all right, first of all, you have to divide this into 2 parts because the 2 lines cross over one another. The one on the left is over here. That integral is going to go from 0 to 1 in the x values, and then this other part will go from 1 to 3. So the left side is integral from 0 to 1 of, the line is on top, so it's going to be the line minus the parabola. So it's 3 minus x minus the one on the bottom, 3x minus x squared, like that. That's the left side. And then maybe I'll just work this one out and then we'll do the right-hand side. So this one, we go 0, 1. All right, it's 3 minus x, distributing the minus sign, minus 3x plus x squared. And put the x's together, I suppose. Doesn't matter all that much. 3 minus 4x plus x squared dx. It should not be a big surprise. Actually, this, you will notice, this is the same as that up there. It's because both of those functions are what you get when you subtract one minus the other one. Sometimes the sign will be reversed, but yeah, not a surprise that it looks the same as that other thing. Anyway, then we just do the integration. So this is 3x minus 2x squared plus 1/3 x cubed, and I plug in 0 and 1. That would be 3 times 1 minus 2 times 1 squared plus 1/3 times 1 minus a bunch of zeros. This is all going to be 0. All right, I saw some people out there actually calculated this. Is it 4/3? I think.
Yeah.
Anyone agree or disagree? I don't really care about that, but some people are trying to flex. I know it's the first week of college. You got to assert yourself, right? 4/3. I walk in here and calculate things. All right, great. And so this isn't the final answer. That's only the area on the left side. Okay, then I'm going to do the area on the right side, which is basically the same. The difference is the integration now goes 1 to 3, and then the functions, when I subtract them here, you subtract in the other order around, which has the effect of just flipping the signs of everything. So the right side goes now 1 to 3, and then more or less the same stuff on the inside, but I'm writing it subtracted in the other way around, like this. All right, this ends up being integral 1 to 3. Everything's the same on the inside, only the signs are reversed. So once you sort of combine everything, it looks like this. And then I'm going to do the integration. It's negative 3x plus 2x squared minus 1/3 x cubed, plugging in 1 and 3. And then this is whatever it is. Can I just, all right. I would expect you to write this out on your homework or something, but just for the sake of getting on with it, everybody knows how to do that. All right, and then the total area is the sum of these two things. Total area is this number, whatever it is, plus that number. This plus this. All right, 4/3 plus whatever the other one was. I think I saw someone calculated the other one is 16/3, if you're into that sort of thing. So it all adds up to 20/3, if that person was correct. All right. Anybody agree or disagree with that number, if you calculated it? I don't actually know if that's right, but somebody did that. Somebody told me that. A whole lot of people are saying it. All right, great. And the other one, let's just talk about the other one. The other one is, I don't know about harder. It's a lot of people were immediately stuck because they set these two equations equal to one another, and then were not able to factor. The one on the left, you should change just ever so slightly and write this as x equals y minus 1 instead, right? Now I have these two functions. If you set them equal to one another, it actually doesn't factor very nicely. Anybody want to suggest why should actually that doesn't even matter. Why is setting them equal to each other not appropriate here? Yeah. Yeah, because these curves are not intersecting, so you're not going to get anything anyway. That's the purpose of setting them equal to each other is to find the intersections. And there aren't any intersections in this case. Really what matters, I don't care about intersections per se, in this example at least. What I care about is where is this, the bottom and the top point. That's going to be the A and the B in my integration. And you can just tell from the picture the bottom one is at 0, right? This is y equals 0, which is my A. And what about the top one? Well, the top one, I drew the picture so that the value on top is the y-intercept of this line, which you can also tell is 1. If you like, you could plug in x equals 0 here to this formula, and you get y equals 1. So this, the top of it, is 1, which is the B, all right? So you don't have to do any kind of set them equal to each other in this problem. Okay, let's see if we can do the rest of it then. Maybe I'll bring this guy down here. Okay, so I'm going to go integral from 0 to 1. That's my a and the b. Remember, I'm doing all of this in terms of y, so I should think about the y value on the bottom up to the y value at the top, which are 0 and 1. And then my subtraction, I go the bigger minus the smaller in terms of x. Can anyone say what's the bigger here? It is the parabola part. Yeah, bigger in this case means further to the right. That is bigger x value. So the bigger one is y squared. So I go y squared minus the other one, which is y minus 1. And it's a dy. All right, this one, maybe I'll just distribute the parentheses or distribute the minus sign. And then this one, at this point, is even easier than the other one. Just the setup is slightly weird. 1/3 y cubed minus 1/2 y squared plus y, and I plug in 0 and 1. So we get 1/3 times 1 minus 1/2 times 1 plus 1 minus a bunch of zeros, and these are all 0. 0. 1/2 times 0 plus 0. Right? 1/3 minus 1/2 plus 1. That's some kind of sixth, I guess, if you want to work it out. Any questions about that one? I hope this has made sense. All right, great. You're going to have some more practice with those on the homework. This is area between curves. And I think it really doesn't get much more complicated than that. Sometimes you have to do it sideways. Sometimes you have to work a little bit to find the intersection points or whatever. But it doesn't really get any fancier than those. Any thoughts about that? All right, I'm ready to go on to the next bit then. So we got like 20 minutes left. So let's talk about a little something else. That was area between curves, the first thing on our big checklist. So just to refresh your memory, we are gonna have homework due on Wednesday, and I already posted the assignment. You can check it out. The assignment consists of some problems of like review problems, basic things about integrals and derivatives, and then there's some u substitution stuff, and then there's some area between curves stuff. And so that homework assignment will be due on Wednesday. On Friday, which is our next meeting after that, we will have our first quiz, and it will have 3 questions on it. One will be like simple derivatives and integrals, one will be the u substitution, one will be the area between curves. And so that's going to be our first quiz. I expect to just do the quiz at the very beginning of class. It'll take like 15 minutes or so. It's just going to be one question about each of those topics. And then I'll have you send in the quizzes on Gradescope, and then we'll just go on with the rest of class as usual. All right? Any questions about how that's going to go? I would like, if you want to, I know some of you get extra time on exams, and if you are, I have already talked to some of you about this. This is slightly weird when it comes to doing these quizzes. Like I just said, I want to do the quiz, immediately go on with the rest of class. Doing extra time in that situation is, I will say, non-obvious. But anyway, I have a plan for that. If you are concerned about the time, let me know, and I will. We'll talk about it. But that's we'll work it all out. But we got to talk about it. All right. Great. Let's go on to the next bit. So this I'm going to start talking about now, but it's not going to be on the homework, and it's not going to be on the quiz until next time around. So this will be volumes. These are sometimes called volumes of revolution. You can use the integral to find volumes of weird shapes. And there are actually several different ways you can use the integral to find volumes, but we are going to focus for a little bit on what they call the volumes of revolution. And there's actually 2 different methods, and there's 2 different lines on your checklist about volumes. We are going to start off by talking about the volumes using the what did I call it the first time?
Washers.
The washers, yeah. Or the discs, sometimes called. The washers is what we're going to do first, and then there's also the shells method. So let's do the washers. We'll talk about the washers today. Here's the idea. A volume of revolution is a 3-dimensional shape that is obtained by revolving a function around the x-axis or around the y-axis. So a volume of revolution is a 3D shape resulting from revolving a function around some axis. All right? Not all 3D shapes are like this, but some are. So, revolving a function around some axis. What I mean, I'm going to try and draw this. I'm not an expert drawer of three-dimensional things, and I won't expect you to be either. But for instance, if my function looks like that, just a piece of a function, you know, as usual, like from A to B, right? If this is f of x, what is the shape that you get when you revolve this? Let's revolve that around the x-axis. What it looks like is, you know, I'm going to sort of spinny this thing. It makes kind of a mirror image shape down here, and it makes this sort of a, you know, one of these, sort of a bugle type shape, I suppose, or a nice prom dress if you look at it sideways. All right. This is the kind of thing that we call a volume of revolution. Not all three-dimensional shapes can be obtained in this way. For instance, like my body is three-dimensional, but my body is not the shape that results from revolving something around the x-axis because I'm too lumpy or something. Like my body is not symmetrical in a rotational sort of way. But like, I don't know, like this water bottle here, more or less is something that you could obtain by rotating a shape around the x-axis. Sometimes I get sucked into YouTube videos of this guy who makes things by turning wood on a lathe. Have you ever seen this guy? He like puts a piece of wood or something on a thing that makes it spin, and then he has this little carving thing that he sticks on it, and it makes a trash can or something. Those are volumes of revolution. Some shapes are like that. Anyway, any shape that is like that, you can calculate its volume by doing an integral. I don't know if the wood turning guy knows this. I imagine it is not a useful bit of information to him for turning the wood. All right, anyway, the usual way. So how do we find the volume? By doing an integral. We can find this volume using an integral. Lots of like standard mathematical shapes actually you can get in this way. Like for instance, a sphere is what you get if you were to rotate a circle around, right? And so you can actually use the integral to find the volume of a sphere. Or other kinds of shapes. We can find this volume using an integral. And the basic idea, it's the same basic idea that we always use in integral calculus, and that is to say, chop it up into little slices. So if I have, I'm going to draw another version of this shape here, this same kind of, come on now, bugle sort of shape here, right? This curve goes around the back too. Okay, if I have this, I want to chop it up into slices. So each slice really looks kind of like this sort of a shape, all right? They are the same kind of usual, you know, rectangular slices that you use when you make an integral, although this time they are three-dimensional things. What can anyone say what would the shape of one of those slices be if I were to like grab it and pick it up with my hands? It's not a rectangle. Yeah? Something like a circle. I would say more specifically, it's like a circle with some thickness to it, right? It's not just, of course, not a two-dimensional circle because these each have some sort of thickness. But anyway, as usual, I would call the thickness of each of these things delta x. And if you were to grab one of these slices and pull it out, it looks like a thick circle. So each one is a, I know I'm supposed to write it that way nowadays, right? A thick circle. It looks like this with some thickness here. Actually, there is a traditional mathematical name for a thick circle. Anybody happen to know? You will feel stupid when I say it. It's a cylinder, yeah. A cylinder, you know, typically we draw a cylinder sort of tall like this, right? But I mean, this is a cylinder, just very sort of short and on its side. All right, so this is a thick circle, also known as a cylinder. It's a cylinder. All right, so really the shape, each slice is a cylinder. I'm going to draw it sort of in the usual orientation that we usually draw cylinders in. Sorry, that's so ugly. Like that, right? So the height, I mean, when I draw it in this way, the delta x, the thickness, is now being drawn as a height. All right? Each slice is a cylinder. And in order to get the total volume of the entire shape, you would just add together all of the volumes of the individual slices, right? This is the whole standard idea of all of integral calculus. So I would like to know what is the volume of each of these slices. Each slice is a cylinder like this, so the volume of a slice is, anybody remember, maybe I'll just on the side here, there is a formula for the volume of a cylinder. Anyone happen to remember? I don't especially care if you do remember, but it's basically, the cylinder volume is really just sort of like the area of the circle part times whatever the height is, times the thickness, right? Is that what you're going to say?
1/3 pi r cubed.
That's the volume of a sphere. Yeah. Yeah, it's the height, it's this pi r squared, which is the area of the circle part times the height. Right? That's the volume of a cylinder. I don't expect that you all have this memorized. Lucky for you, because apparently you don't. That's the volume of a cylinder. So anyway, what would I do? What's the volume of a slice then? Well, apparently it will be pi. I'm writing pi r squared h. Well, I'll just write that first of all. Pi r squared h. Now, pi is just pi. H, in this case, is delta x, right? That's the height. And what is r? Can anyone say how? R, of course, is, the radius of the circle, which is right there. How can we find r given the setup that we have here? You have to kind of remember where all of this comes from. Yeah? It is f of x. Yeah, r is just the distance from on our original picture, the distance from the middle up to the edge. And that is the height of the function, which is, the y value, which is f of x. So this here, actually on this picture, that distance right there is f of x. It's now sideways, but it used to come from a vertical distance from the center of the rotation axis up to the curve. So a volume of a slice is pi r squared h, which is the same as pi times f of x squared times delta x. All right? That is the volume of an individual slice of this thing. And so what's the volume of the entire thing? It's the integral of this, and I change delta x into dx. All right? It's exactly the same as this area between curves thing. When you have a sum of a bunch of little bitty bits, they become an integral where the delta x part becomes a dx in the integral. So this is the total volume, and this is the formula that you will need to memorize, I guess. It's not a hard formula. It is pi f of x squared dx. This is the total volume of a volume of revolution. So usually I'm going to write this, I suppose, very slightly differently. The pi is a constant on the inside of the integral. You can always factor the pi out of an integral. So I'm pretty much always going to write this formula like that. Just because pi being a constant can always be factored outside of the integral. And here, A and the A and the B are the boundaries of the region that we're talking about. So remember, where the A and the B comes from is, we always begin with some function like this, right? From A up to B, and it gets rotated around. Something like that, right? So the A and the B refer to the leftmost end and the rightmost end. All right, and let me just say, this is for revolving around the x-axis. All right? This is the simplest version of this formula. We're actually going to do some variations of this which revolve around a different a different, say, horizontal line, or perhaps even revolving around a vertical line, and you'll have to modify the formula a little bit in those other scenarios. But anyway, this is the simplest version of the volume of revolution formula. This is for revolving a function around the x-axis. All right, let's just try an example, and maybe that'll do it for us for today. Next time, maybe we got 2 examples. Yeah, let's do 2. And then next time we'll do some more fancy versions of this. Any questions so far, though? So, like everything that I said up here is kind of a derivation, or this is why the formula works. I would say, for the sake of doing the problems correctly, you need to know this formula. I suppose it's not strictly necessary you know where it comes from, although I hope everybody was able to follow all of that. Okay, let's try the volume of this sort of bugle type shape. This is y equals x squared, and I want the volume from 0 to 1. So that curve, but revolved around the x-axis. So it's going to look like the sort of 3-dimensional shape you get. Looks kind of like this, right? This sort of bugly thing. Remember bugles? The snack? I'm into those things. Tastes like nothing, just salt. Classic. All right. I want the volume of that from, and this is x equals 1 over here. The volume of this. All right? This is a very simple one. You just basically plug it directly into the formula up there. All right? I have my function is x squared, the a and the b. What am I going to use for the a and the b here? Yeah, 0 and 1. It's the x value all the way on the left and going up to the x value on the right, which is 1. So there's really not much to this one. I put pi just because. If someone asks you why you got to put the pi there, one answer is just because. That's part of the formula. Although if you want to really explain, it's because basically this formula is based on adding together a bunch of circle areas, and so you have pi r squared is essentially what that formula is. Only it's couched inside an integral to give them the thickness. All right, I go 0 to 1, and then f of x, the whole thing squared. Make sure you get all these squares in there, right? It's like that. In this example, f of x is x squared, and then there's a square already in the formula, so we need x squared squared. All right? And what do? X squared squared is the same as x to the 4, so this is pi integral of x to the 4 dx. And so we do the integral for x to the 4th. It's 1/5 pi over 5, x to the 5, 0 and 1. And we plug in 1, we get pi over 5 times 1, and then we subtract pi over 5 times 0. Answer is pi over 5. A strange answer. Again, it makes me think, if I somehow took 5 of those bugles, I could put them together and get pi? I don't know. You couldn't really put 5 of them together in a sensible way. But all right, that was an easy example. Let's do one that's a little bit more interesting. We got 5 more minutes. How about, as I mentioned before, a lot of the sort of ordinary, like classical 3D shapes in geometry can be viewed as a volume of revolution. Let's try, how about a sphere? Find the volume of a sphere with radius 2. All right, now, at some point in your youth, you learned there's just like a formula for this. Actually, somebody said this a few moments ago. Its volume is 4/3 pi r cubed. That's the formula for the volume of a sphere. If you plug in 2 here, that's going to be 8, and then times 4. This is 24 over 3 times pi. If I plug in r equals 2, r 2 cubed is 8, and then that. So anyway, this is what the answer is supposed to be. But I want to do this not using the old memorized formula, but actually by calculating in terms of a volume of revolution. In fact, that's where that formula comes from. You can actually derive that formula entirely as a revolution of a circle, right? The sphere is what you get if you had a circle and spin it around the x-axis. So we must, so that right there, this is kind of like the back of the book. That's what the answer is going to be if we do it correctly. We must revolve a circle, right? Now, one thing immediately slightly weird about this is we really want it to be a function that we revolve. A circle is not a function. So I'm just going to take the top half of a circle because that's actually good enough if my intention is to revolve it around the x-axis. I don't need the bottom half, right? So I'm actually going to use just the top half of a circle. This we have to write as a function. Any ideas about how to do this? Anyone remember like the formula for the circle? I want the circle of radius 2, of course, because that's what I said before. Anyone recall this, the formula for a circle? Yeah? It would be, yeah, she said x squared plus y squared equals r squared, right? So in this case, I want radius 2, so I would do x squared plus y squared equals 2 squared, which is 4, of course. And then to write that as a function, we would solve this for y. So this would say y squared equals x squared plus 4, right? And then solving for y means I do a square root on both sides. Square root x squared plus 4. I always feel a little nervous when I take a square root. Do I need the plus or minus or whatever? And usually the answer is, well, technically yes, although I only want the top half, so actually I only want the plus, not the plus or minus. Minus 4, yeah. No, minus x squared. Sorry, I just put it over there. It should have been subtracted. Thank you. 4 minus x squared. It matters, folks. 4 minus x squared. Thank you. Okay, that's my function. Since I didn't do the plus minus, I'm only getting the top half, but that's okay because that's all I want anyway. All right. Okay, that's going to be revolved. What are the A and the B? That's the sort of leftmost and the rightmost end. What do you think? Minus 2 and 2, right? This is supposed to be a circle of radius 2, so the point over here should be a minus 2, and the point over here should be a 2. All right, I think I'm ready to draw my integral. So it's minus 2 to 2. Pi on the outside. Remember, the formula is basically pi times r squared, but with r as f of x. So this is my function, 4 minus x squared, squared, right? This is my formula. Plugging into the formula. I didn't like the looks of that square root, but I feel good about it now because it's getting squared anyway. So this square root squared will go away. Yeah?
Since it's a semicircle, could you do 2 times pi times with like the integral just going from 0 to 2, since it's the same on both sides?
Yes, you could do that if you want to. Yeah, she said, could we just start at 0 and go out here and then multiply the whole answer by 2? And I say, yes. I don't know if that's any better than just doing it this way, but yeah, that would certainly be correct. Let's just finish this off. I know it's time to go. So I do the square first. I get pi minus 2 to 2. Square the inside, which kills the square root sign. It'll say 4 minus x squared. She's having trouble hearing me. It's because she's in your pocket. Keep her in your pocket. Okay, and now I got pi on the outside. Just do the integral. This is an easy integral. Sorry, I'm trying to do this quickly just because it's time to go. Plugging in 2 and negative 2. Can I just say, etc.? This, you will eventually, would you believe me if I said, you get 24 over 3 times pi. Where'd the over 3 come from? It comes from right here. And then when you do all the other numbers, you end up with 24 over 3. All right, have a great weekend. Let me know if you have any questions about the grade scope or any of that. And please talk to me if you're concerned about time on the quiz. See you next time.
Have a weekend.
See ya.